Thank you very much, Marie-Claire. Good evening. So it is my pleasure to invite you in this journey from Earth to Jupiter under auroral lights. So in the first part, I'm going to focus on aurora at Earth, and then I will be introducing you to Ganymede, the largest moon of Jupiter. Both the moon and the planet are hosting aurora. But first, what is an aurora? So as any of you already observed aurora? I see a few hands, and that was impressive. Yeah, I mean, aurora has been capturing human imagination for centuries. There are a very rich folklore associated with the aurora. For instance, the red light was thought to be the spirit of warriors who, after death, were continuing fighting. Or as illustrated on the right here, the Inuit sculpture described the aurora decapitating somebody. Aurora are harmless. But why this fascination? Well, the auroral light can take a huge part of the sky, but that's not the most fascinating thing. The most fascinating aspect of auroral light, and perhaps we can dim it a bit, that's the fact that they are moving, they are changing, they are dynamics. They are called sometimes the dancing lights. Even when they are relatively quiet, and we can dim it also for this one. Auroral emission can be quite unsettling because they are changing. The first time I observed aurora was in North Norway, and I was outside during the night. It was snowy, so it was already a bit spooky. I was alone. And then I saw this green line, and it was like a hand, which then developed over a few minutes and took a large part of the sky. I knew it was light, so I stayed, but at that very point, the first time I ever observed such an amazing event, I understood all the myths linked to the aurora. So auroral emission, they appear like draping curtains, usually, but sometimes it feels like they are converging towards a point, as we can see here on the two pictures on the right. That's just an optical illusion. Like when you see a skyscraper from far, they appear parallel, but if you are in the middle of the city, then you feel that they are converging. So where are we observing usually auroral emission? That's in a region which forms an oval around the magnetic pole. So typically it's above the northern Scandinavia, Iceland, south of Greenland, Canada, Alaska. And therefore that's populated region. And they were historically then reported, people were reporting aurora from this region in the northern hemisphere. So the emission observed there are referred to the northern lights or the aurora borealis. So aurora is by analogy of the light at dawn, which is light red, as one of the key colors of the aurora is also red, though the process is totally different. And borealis, which refers to the northern hemisphere. But since the space age, we can observe aurora borealis as often as aurora australis over the southern hemisphere or southern lights. But historically, they were much less reported, and is the reason you usually hear aurora as the northern light, because the auroral oval that we see here on the lower right is primarily over the Antarctic Ocean, so uninhabited region. So as seen from space now, so we're looking at the aurora from above, from the International Space Station. So that's a sequence of photographs, which then allow to have this movie. And we see the two dominant lights of the aurora, the red line and the green line. So how are those emissions produced? So let's consider an atom or a molecule in the upper atmosphere, so nitrogen or oxygen. It can undergo a collision with an energetic particle, for instance, an electron. And then this electron can excite this atom or molecule. That's the excited state, that's an unstable state. And you can't stay excited forever. You need at some point to relax. And one way to do that, it's a radiative transition, so by emitting a photon. However, for this light to be considered as aurora, we need ultimately the source of energy which generated the aurora to come from outside the atmosphere. So those electrons or ions, they have to come from outside, and therefore aurora is a tracer of plasma interaction with a body, with here the Earth, or a planet, a moon, or a comet. So to summarize, aurora is the photo manifestation, photo because they are produced not only in the visible, but also in the X-ray, in the ultraviolet, all the way to the infrared. So the photo manifestation of the interaction of energetic extra-atmospheric particles, typically electron and ion, with an atmosphere. So any body in the solar system, be it a planet, a moon, or a comet, which has an atmosphere, if it's bombarded by particles which come from the space environment, are going to exhibit auroral light. And this light is also a fingerprint of atmospheric species. So I mentioned that the major two colors are the red and the green lights. So what are they? They're actually emission lines from the atomic oxygen. So the green line is at 557.7 nanometer, and the red line, it's at 630 nanometer. Sometimes in the lower boundary of the auroral curtain, we can see a violet line that's actually from nitrogen. So if we can decompose the light of the aurora, we will see not only the atomic oxygen emission and occasionally this violet line from nitrogen, but we will see a large range of emission also from molecular oxygen, atomic nitrogen, and so forth. So what I propose you to do now is to make an aurora here in this amphitheater. So how are we going to proceed? So I have here a tube which includes a gas. And what I'm going to do is that I'm going to, when I'm going to turn on this apparatus, current is going to go through, and therefore electrons are going to go through the tube and excite the atoms which are present. And then those excited atoms are going to de-excite by emitting light. So we are going to do our own aurora. Now, let's be a detective. I mentioned that auroral light is a fingerprint of the atmospheric constituent. So I've put here the spectrum of sodium, hydrogen, and mercury. So atoms can only absorb energy, a certain amount of energy, only certain values are allowed, and then it's then going to emit lines, emission lines, at specific wavelengths, at specific colors. And this combination is unique to the atom. So I'm going to encourage you then to now use the glasses. If you don't have one, please share with your neighbor. And, or ask Marie-Claire. And I'm going to ask you to be a detective. I'm going to turn on the light, and you will have to tell me what is the gas which is in the tube. Is it sodium, hydrogen, or mercury? Are you ready? Ready? Yes. Okay, so let's dim the light. Thank you. Okay. So I'm going to turn it around so that people can do it in turns. So I'm trying to turn it here around for everybody to see. Okay, so what was the gas included? Anybody? I hear different thing. So that was mercury. So actually, some of you may remember the street light when there was a mercury bulb which was used, and it was slightly green. So here on the spectra, which are shown behind me, you have all the lines of the same intensity, but actually some lines are stronger than others. And one strong line here in the spectrum of mercury, that's the green line, and those street lights indeed often look a bit green. So now I'm going to do another. So it's very warm, so it's the reason I have to use a glove. And put it here, such that the plastic doesn't melt. And do you want to do another aurora? Yes. Great. Okay. Are you ready? Yes. Excellent. Let's go. So let's dim the light. Thank you. So I will start here and then turn it around. Then I'm going to turn it back. So again, atoms can only absorb energy at certain values and then emit light at certain wavelengths, at certain colors. It's the reason why, I can perhaps keep it a bit longer here. I have to turn it, I can't have it on more than a minute, so it's the reason I'm under time constraint here, because it gets pretty warm. Okay, so what was in the tube? What was our aurora here? Yeah? Yeah, hydrogen, yes. So if we would have an atmosphere made of hydrogen, then we would have the aurora red. Okay. So now we have understood, we have looked at the origin of the light. It's emitted the red and the green light, its emission lines from the atomic oxygen. But as we can see from this picture taken from the International Space Station by actually Tim Peake, we have the green below the red. And at which altitude, actually, those emissions are occurring. So the green line is emitted above 100 kilometers, which is the distance from here, the Royal Institution, to Oxford, except vertically. And it's well above the clouds. So the clouds are typically from up to about 10 to 15 kilometers. So on average, the distance from here, the Royal Institution, all the way from the Royal Observatory of Greenwich. So if it's clouded, you can't see the aurora, except if you are lucky. And one day after an auroral campaign, I took off from Fairbanks, Alaska. It was clouded. It was night. We couldn't see the aurora due to the clouds. But then when the plane reached cruise altitude, here through the window, we could see the aurora. So what a treat. Now, I didn't explain, before to move on, why the red line is above the green line. So the red line is produced above 200 kilometers. At that altitude, the dominant neutral species is actually atomic oxygen. And the red line is a direct excitation by electron of the atomic oxygen. So it's an electron collides with the atomic oxygen, the atom goes to an excited state, O1d, and then de-excite, radiative de-excitation from O1d to the fundamental state. However, the radiative lifetime of this excited state is relatively long, 110 seconds. So while it can naturally occur at above 200 kilometers, when you go at lower altitude, at 100, 150 kilometers, the atmosphere is denser. You have more collision. And therefore, the de-excitation of the excited state doesn't occur through radiative emission, through the production of a photon, but through collision. So the reason it's not occurring anymore. While for the green line, the excited state, O1s, has a radiative lifetime much shorter, less than a second, and hence, even at low altitude, it can be produced. However, it's a higher excited level, and it's actually not produced directly by electron impact. It's mainly produced, electron is colliding with N2, and then N2 is an excited state and collide with O, which then lead to this excited state. And so it's not occurring at high altitude, but at lower down. Of course, high, low, it's all relative. But again, you need clear sky to be able to observe the aurora. Great. So now we have those emissions. We know how they are produced, where they are produced, but what is triggering the aurora? Why do we have them at high latitude region only, and where is this energy coming from? Well, all comes from the sun and the interaction of the sun with the Earth and its near environment. So the sun produces not only light, but also particle, plasma, electron, and ions. And what we are seeing here, which is the sun is just on the left, it's light scattered by the solar wind electron. If you wonder, yes, there is also a little comet Encke, who got hit by a coronal mass ejection. But you know, you don't need a strong event to have aurora. Aurora is occurring all the time. Sometimes it's subvisual. The solar wind is a continuous flow from the sun. Now, when this plasma comes in the near environment of the Earth, what's happening? Can they reach all the way to the surface? No, because the Earth has a global, permanent magnetic field. So what is a magnetic field? So what I have here is a magnet, just in case you don't trust me. That's a magnet. And we can't see the magnetic field line. Can't see them. But Michael Faraday, in this very institute, had the idea. We can reveal them thanks to iron filling, which we are going to do now. But for you to see, I should put, here. Okay, so let's pour some iron filling here. So that's the same experiment that Michael Faraday. Oops, did I put a bit? It's an experiment, right? It's always tricky. Of course, I did it just before it was perfect. Let's try again. I have to put some, but not too many. But enough at the same time to reveal the magnetic field line. Yes, we can start to see them here, and we start to see them over there. So we see magnetic field line here and here. So what happened is that the iron filling fill the magnetic field, at least the electron in the atom, and then get oriented like get oriented along the magnetic field. So we can see. So this experiment allows to visualize the magnetic field line as it's shown here on the left. And similarly, the Earth, except that it's not a magnet, but it's in the outer core, we have melted iron and nickel, which generate a global permanent magnetic field. But the configuration of the magnetic field line is very similar to our little magnet here. So it means that let's recap. We have the sun, which is emitting not only light, but plasma. So we are looking here at the plasma, electron and ion, many proton. When they come in the environment of the Earth, they have to go around this magnetic shield. They can't penetrate it, except in regions which are actually magnetically connected to the auroral region. So they can penetrate in this specific region, and it's the reason why then we have the auroral emission which form an oval. Now, this oval is typically, as I highlighted earlier, over the high latitude region. So over the northern hemisphere is typically over North Scandinavia, Iceland, Greenland. So, what's happened the past year? What's going on? 3 times we were able to see the northern line from London. That's rare, so it made the front page news. Unbelievable northern lights display illuminates night sky over London. May 2024, again October 2024, then January 2025. Has any of you actually observed the aurora over London? One of the, okay, 1, well done. 2, 3, actually, a few of you. That's great. So, can we do that today? Well, I checked, sorry. For tonight, low activity. You have to go to Norway, so you have to hurry. Even mid-June, we had a bit more magnetic activity, but still, you know, the auroral index varies from 0 to 9. Here at mid-June, we were level 6, and the auroral oval only goes to North Scotland. So, what happened? Here, Hammersmith Bridge, October 2024, the red line. It's unusual, but it happened. So has it often happened in the past? Well, it's rare, and therefore it's more frightening to people, all the more that from more south latitude or equatorward latitude, you mainly see the high altitude aurora, so you see the red one. So in 1583, very strange sights seen in the element, the atmosphere, over the city of London, bloody colored with streams like sharp spear, fearful to the beholders. An aurora on the top left, we have an aurora over London, or near London, it's Guildford. Then in Japan, again, that's red aurora. Over France, Paris in fire. So they thought it was plague or war. It was bad omen because it was rare. Well, it has nothing to do with omen. It has all to do with the sun and the magnetic activity of the sun. So what we're seeing here, it's over 11 years, the picture of the sun in the X-ray, which reveal its magnetic activity. So the sun has an 11-year cycle between solar maximum, when it's very active, and solar minimum. What is shown here on the vertical axis is the number of sunspots, which is a proxy for the auroral activity, the solar activity, as a function of years from 1990 to 2030. So 2025, here it's the cycle 25, we are at solar maximum. What does it mean? Well, and why do we have this cycle? So at solar minimum, the sun, like the Earth, has a nice dipole, similar to our own feeling, which revealed the magnetic field line. But the problem is the sun doesn't rotate at the same speed I mean, the speed at which the sun rotates depends on the latitude. It rotates much faster at the equator than in the higher latitude region. So in 25 days at the equator, up to 35 days, so much slower, near the high latitude. So over time, it becomes a mess. And the magnetic pole moves equatorward. So what happens every 11 years is that the magnetic north and south pole swap and then swap. So truly, if you want to be exactly in the same configuration, you have to wait 22 years. But between two solar maximum, which we care about, that's 11 years. So what happens then? It doesn't mean you will see aurora every night during high solar activity, but it's more likely to have a big, huge solar eruption, like a coronal mass ejection, which is shown here on this movie. Again, that sunlight reflecting on the electrons. It may hit the Earth or not, but if it does, it's going to perturb largely the magnetic field, and then the auroral oval, the equatorward edge of the auroral oval, is going to move all the way to the red line, which actually covers London. So, great. Auroral emissions are quite fascinating. They are moving, they are changing. And sometimes we even don't need to go in high latitude. They treat us well over London. Great, that's fun. Well, auroral emissions are not only fun, but also useful. So as mentioned earlier, it's a fingerprint of the atmosphere. And when we look aurora, not only at Earth, but elsewhere, it can be quite, it's a way to, in a remote sensing way, to probe the composition of the atmosphere of other solar system bodies. But auroral particles, they not only, when they collide with a neutral, with an atom or molecule in the atmosphere, they not only can excite it, which lead to the auroral emission, but they can also ionize it. And that increases the plasma density in the upper atmosphere, which can affect, for instance, communication between the ground and high altitude satellite, like, for instance, the geostationary one. So we can use actually the aurora spectroscopically, quantitatively. We can analyze it to go back to extract the information about the incoming particle which was responsible for them. And you can say, yeah, but why bother? You take a satellite and it goes over the auroral region, you measure them, what's the point? Well, you can actually take a snapshot of the auroral emission and you get the whole oval in one go. And then, with modeling, we can infer all the other perturbation. And that's really important because while the aurora is not harmful, the electrons which are responsible, or protons, which are responsible for auroral emission, generate other perturbation, which can affect, I mentioned technologies. I mentioned communication, for instance. It can also generate current in the upper atmosphere, then induced current in the ground, and that, for instance, led to the blackout in full Quebec, in the whole Quebec region in 1989. So that refers to space weather. Space weather is the dynamic condition at the sun, in the interplanetary medium, and in the near environment of the Earth, which can affect human health and technologies. And we rely more and more on technologies. So some extreme space weather event, some extreme solar event can then disrupt satellites. When you dump a lot of energy into the atmosphere is going to expand. If you hit a balloon, it's expand. That's similar, and so low-altitude satellites are going to be perturbed. You can lose satellite. It can disrupt also electrical power grids and communication system, impacting the navigation. So the UK has actually put extreme space weather events on their national risk register. And there was the Met Office Space Weather Operations Center, which was created to be able to monitor and predict space weather. Okay, so that's our journey on Earth. But I mentioned that the aurora, it's light which is emitted when electron or proton or energetic particle bombard an atmosphere. So we could expect to have auroral emission throughout the solar system as long as the planet, the moon, or the actually comet, when it's close enough to the sun, has an atmosphere, even escaping atmosphere for comets. So here's again the auroral oval of the Earth. This image and all the ones I'm going to show here are at least of the aurora, or auroral oval, have been taken in the ultraviolet, so we can't see that, it's not visible. Therefore, it's in false color, so that we can see something. And here we have Saturn and Jupiter. So the background picture of the planets is visible, but the auroral oval that you can see in blue for Saturn and in white for Jupiter are in ultraviolet observation. And they have also an oval because they have also a global magnetic field. But the way actually the aurora is produced is a bit different. For Jupiter, we say that the auroral oval at Earth is the result of the interaction of the Sun with the Earth. But for Jupiter, those emissions are within the main oval. And the main oval is actually the result of breaking from co-rotation, the Jupiter being a fast rotator rotating in 10 hours. We can see also the footprint of some of the moons, Io, Ganymede, and Europa. And those footprints, those auroral emissions in the atmosphere of Jupiter, they are magnetically connected, as it's illustrated on the figure on the far right, to the moon. So the moon and the footprint are linked together through the magnetic field line of Jupiter. So we can learn a lot about plasma interaction by analyzing those emissions. Now, what about Mars? So Mars is a different type of aurora, but as it doesn't have a global magnetic field, only some remnant over the south hemisphere, there is no auroral oval. So for instance, for the diffuse aurora, then you will have emission not localized specifically. But now, what about Ganymede? Ganymede, which is a moon of Jupiter, is the larger moon in the solar system, larger than actually planet Mercury. So it was discovered by Galileo, and so they are referred to the Galilean moon Io, Europa, Ganymede, and Callisto. So those drawings here, they are drawing from Galileo from observation he made in 1610. The circle represents Jupiter, and the asterisks are some light he was observing. And those little points of light, which are the first drawing, by the way, that have been reported using a telescope in the sky. And you can see that those asterisks move from day to day, from night to night. So from one night to another, their location with respect to Jupiter is changing. So what are they? Well, we can actually, through simulation, we can recreate the configuration, the location of the moon at the time in 1610, and here it is. And it fits fully what, based on the drawing of Galileo. You don't see always the very far left moon because it's out of the field of view. But what is the most remarkable is not that Galileo had actually the curiosity. So if you have curiosity, I mean, I see a lot of kids, please keep your curiosity. Ask yourself questions. He had the curiosity to use his telescope not to see the battle in the other side, which was originally the spy glasses were used for. He adapted to actually look at the sky. And he looked at the sky with an open mind. And not only he observed those point of light which was changing night to night, but he had actually the idea, he realized that they were moons, which was revolutionary in 1610. But what do we know about Ganymede? It is an icy moon, so it has an icy crust, water ice. Not pure, but it has water ice. And it has a thin atmosphere composed of oxygen, O2, water, hydrogen. And it has aurora, but wait, it has not only auroral emission that here have been observed from the Hubble Space Telescope in the ultraviolet, but that's auroral oval. What does it mean? It means that Ganymede has, as Earth, Jupiter, and Saturn, a magnetic field, a global magnetic field. Actually, Ganymede is the only moon known in the solar system to generate a global magnetic field. And that was discovered by Margaret Kivelson, who was the PI, I'm the principal investigator, for the magnetometer on board the Galileo probe. So the Galileo spacecraft was orbiting Jupiter and did flybys of the moon Ganymede. And from those measurements, she derived that, she made the discovery that Ganymede generates its own global magnetic field. But data didn't, when you take into account a dipole, didn't fit fully. And she thought perhaps there is another component. And this other component may be a subsurface ocean. Later on, so again, those auroral emissions are observed from the Hubble telescope. It shows oscillation, and you expect that the oval oscillate. On the right, what is shown is, so I mentioned that Jupiter is rotating in 10 hours, and its magnetic dipole axis is tilted of 10 degrees compared with spin axis. So as the planet rotates, the magnetic field experienced by the moon, and the central one here is Ganymede, is changing. Therefore, you expect to have the auroral oval oscillating over time as Titan rotate. But this tilt actually was much smaller than anticipated. And again, consistent, the smaller tilt than anticipated, consistent with the presence of an ocean. Second evidence. So, what's the significance of that? We have this, Ganymede has this icy crust, and below we have this subsurface ocean. And then below that, we have the icy mantle and rocky mantle, and ultimately the liquid core would generate the global magnetic field. That's cool, but is it just cool? There is some implication here on the habitability, because the habitable zone is roughly around the distance from the sun, heliocentric distance, it's around the Earth up to Mars. If you are too close to the sun, too hot. If you are too far, too cold. But that is the habitable zone on the surface. But we have discovered, or it's very likely, depending on the moon, that there's subsurface ocean on a large number of moons at Jupiter, Saturn, and even Neptune. So that extends the possibility to find life. So I'm not saying we have found life in the subsurface ocean, but what I'm saying is that there is potential far away from the sun to still have life in the subsurface ocean, even though you are far from the sun, and even though those moons are undergoing a huge radiation on their surface, because then life would be isolated, will be protected in the subsurface ocean below the ice sheet. But how to detect the subsurface ocean? And why did we have this signature that we saw from Galileo, or that this rocking of the aurora was less than anticipated? Well, all comes to Michael Faraday experiment that it did in this very building. And if you have not done it yet, please go and visit his laboratory. So, as I mentioned earlier, the magnetic field of Jupiter is changing with time at the moon, so here at Ganymede. And what does it mean if we have a changing magnetic field? That's what we're going to see in a minute. So I have a little experiment here. Yeah, thanks. So I'm just showing, I have a coil of wire here, and then it's connected to a multimeter, and I'm going to use a multimeter to measure the current, so I have an amperemeter, and then it's back to the coil of wire. So there is no active element here, it's all passive. And we can see that when I'm going to turn it on here. 0, no current. Okay. So, I have a pen here. I'm bringing into the coil, into the coil. Is something happening? No. Now, I'm going to use a magnet, if you don't trust me. So this magnet generates magnetic field. And so I'm going to put it in and out. Is something happening? Yes. And if I leave it inside? Nothing. If I wait long enough and if I don't tremble. But if I move it, however, it's changing. So the key things here, we have a changing magnetic field. And what Faraday showed, thank you very much, is that a changing magnetic field generates an electric field. Even if you have no charges, I mean, some of you will know that we have a charge, static charge, it will generate an electric field. Here, with the absence even of charges, we create somehow, yes, ultimately we need charges to generate the changing magnetic field, but we create a change in magnetic field, and at that location where there's no charges, nothing, you will have an electric field which is generated. So of a nature very different compared with the electric field which is generated by a charge. And if at that location you have free charges, like here in the conductor, in the wire, then you are going to have a current because you are going to experience the electric field. So going back now to Ganymede, we have this ocean, subsurface ocean, and it's salty on the surface. There is evidence, most potentially there is salt. So it's and also when we compare with Enceladus, a moon of Saturn, which are cryovolcanology, and that was those geysers were sniffed by the Cassini spacecraft. There is salt. So if we have salt in water, you have iron. We have iron, and I just say we have a changing magnetic field, so we have therefore a current. That's the first step. Now, we have a current, great, we have a current in subsurface ocean, but we can't drill through the ice sheet. So how are we going to still detect this subsurface ocean? Well, Ørsted discovered that a current generates a magnetic field. And André-Marie Ampère then studied it experimentally and then tried to describe it mathematically. And what he showed is that, so here we have an horizontal bar, and below we have a compass, which is experiencing the magnetic field of the Earth. And then there is wire, which ultimately goes to a battery. So when we turn on the current, the compass needle is moving. And then when we turn off the current, then it goes back to the origin. So it highlights that a steady current generates a magnetic field. Huh! So let's go back to our ocean here. Subsurface ocean. We have a changing magnetic field which generates an electric field, and we have iron in this ocean, so we are going to have a current. And this current is going to induce a magnetic field. And this magnetic field, that was the last component that Margie Kilvelson identified in the data. That's also because of this induced magnetic field that the oscillation of the auroral oval is less than anticipated. The best way to characterize a subsurface ocean is to make as many measurements as possible of the magnetic field around the moon. But it's going to be challenging because Ganymede is bathing into the magnetic field of Jupiter, which is extremely intense. I mentioned also that Ganymede generates its own magnetic field. And on top of it, here, one of my PhD students did the simulation of iron. So I mentioned that Ganymede has an atmosphere, and this atmosphere is partially ionized. And those ions are also going to contribute to the magnetic field. So it is not trivial to extract the induced signature of the subsurface ocean, but it is the best way to do so, because we can't drill through the ice sheet, is through magnetic field measurements. And that's exactly what the Jupiter Icy Moons Explorer is going to do. So I was lucky enough to be able to attend the launch of the Jupiter Icy Moons Explorer from French Guiana in South America on the 14th April 2023. So a special moment. I've been involved in this mission, not on the hardware, but on the science from the beginning, quite some time ago. So where is JUICE today? It's actually close to the orbit of Earth. So what we see here, we have the Sun, and then the first circle is the orbit of Mercury, then Venus, Earth, and the last one is Mars. So what is the plan? After the launch, we had actually last summer the first ever flyby of a gravitational assist of the Earth and the Earth. Okay, let me rewind. The spacecraft is not going directly to Jupiter. It's actually using help from planets to gain momentum and ultimately reach Jupiter. And usually we use a planet, but last year that was the first time ever that a space mission used both the Earth and the Moon. This summer, it will do a flyby of Venus before to have two flybys and ultimately arrive in Jupiter in 2031. But then it will do a Jupiter tour. So it will be in orbit around Jupiter, flying by, like Galileo, the Galilean moon. But the coolest things is that at the end of the mission, it will go into orbit around Ganymede. And so it will be able to gather all of those data needed, especially from the magnetic field, to infer some constraint, for instance, the depth or the salinity of this subsurface ocean. So there is a very rich payload on JUICE. I'm not going to go through all, but you have a UV spectrograph, imaging spectrograph, which will be allowed to look at the aurora, not only at Ganymede, but at Jupiter. And you have also the magnetometer, which was actually built at Imperial College London, so my home institute. And as I mentioned, plasma around will also be influencing contributing to the magnetic signature. So you have an instrument which will be measuring them, among others. And what is the goal of JUICE? It has 5 goals, and among those 5, 4 are associated with Ganymede. So why is Ganymede so unique? It is a fascinating moon, an icy moon with a subsurface ocean and the only moon in the solar system to generate its own global magnetic field. Larger moon, a dimension larger than Mercury, and have this cool auroral oval as well. Then what are ocean worlds like? And that's all the icy moon, not only Ganymede, but also Callisto and Europa. But having the orbit around Ganymede will be quite critical. Then how has Jupiter complex environment shaped its moon and vice versa? And the last one linked to the moon is, could there be or ever have been life on Jupiter system? So the goal of JUICE is actually not to identify life, but really to constrain the habitability. There is also some goal on Jupiter I'm involved in, but this here focusing on Ganymede. So take-home message. Aurora on Earth. Look up in the coming year. I can't promise, but it's maybe that we are treated by another auroral display over London. And then as for the aura on Ganymede, so on this fascinating moon, aurora, I mentioned, is the fingerprint of atmospheric species. It's a tracer of plasma interaction, but actually it was used also to probe the internal structure of the moon, and was another evidence of the presence of a subsurface ocean. Thanks to Faraday's experiment, which was first presented in this, to the public in this very special lecture theater, then we have seen that we can use this result to constrain the subsurface ocean at Ganymede. As for the Jupiter Icy Moons Explorer, which is en route to Jupiter, it's the first European mission towards the outer solar system. First flyby last year of Earth-Moon for gravitational assist instead of using just the Earth. First mission, ultimately, in 2035, to orbit a moon of the solar system, except our own moon, of course. And I didn't mention, but actually, in addition to the European Space Agency mission JUICE, there is also a NASA Europa Clipper mission, which is en route to Jupiter, which was launched in October last year and will arrive in 2030. So, and both are interested, among others, to the ability to try to constrain the habitability of the icy moons. And on the figure here, you can see the orbits in blue of Europa Clipper and in red of JUICE for combined observation. So stay tuned. Thank you very much.